Welcome to the fifth lecture in Lattice Boltzmann methods in winter 2022. Today is, as always, some important topics about the understanding what we are actually doing here. And in particular, we will ask the question, why is it a good idea to use kinetic methods to solve the Navier-Stokes equation, because this is obviously not very obvious. So we're talking about the implicit collision operators. This is at least the first part of the lecture, and then we'll also come to discrete equilibrium functions, and then at the end we'll also introduce ghosts and aliens. I think probably ghosts we have already introduced. I don't remember. Okay, so the first thing today is the over-relaxation as the big topic, and the question that we are asking here, as I just said, is why is it not insane to solve the Navier-Stokes equation with a kinetic method? Because if you talk to people who are studying kinetic methods, they will usually get very angry on you if they heard that you do Lattice Boltzmann, because they consider this insane. And they have a very good reason, and the reason is that if you use a kinetic method, I mean the Boltzmann equation, if you base your research on your simulation on the Boltzmann equation, then the Boltzmann equation is of course related to the collision of particles, and in order to simulate this, you have to resolve the time scale of the collision of the particles. Okay, so what is the time scale of the collision of particles? Let us have a look with an order of magnitude calculation, what this actually means. So we do an order of magnitude calculation, starting with what is the mean free path in air. Okay, we take air as an example. This is not important, but air is something we often live in, right? So the mean free path in air, I think I said this last time, is about 16 nanometers. Yeah, this is the mean free path, and then we have the speed of sound. So speed of sound is very closely related to the speed at which particles are actually moving about. So speed of sound, say in air. So what would this be, speed of sound, roughly? Yeah, 340. Huh? 340 meters per second. Okay, and then from these two things, so we have the path that a particle can move, and we have the velocity with which it moves. So this gives us the mean time between the collisions, which we call mean free time. So mean free time is about the mean free path divided by the speed of sound, and you see that this is 0.17 nanoseconds. So billions, so 10 by the power of minus 10 seconds. So we need 10 billion time steps to simulate 1 second, right? That's a lot, yeah? Okay, but only under the assumption, by the way, this was not, okay, this doesn't mean that this would be the time step, because what we have, this is the time that we would have to resolve, because the collision time, the time that the collision takes, is of course much smaller than the mean free time. So it's even worse, right? So, and of course this means that kinetic methods, depending on what you want to do with them, but if you want to simulate your car, for example, which is often done with Lattice Boltzmann, then you see that this requires a prohibitively short time step, right? So this means we are doomed. But apparently people are using this, so somehow there must be a solution. And the question is whether Lattice Boltzmann actually has this problem. And of course, it turns out that we don't have this problem. So there are different collision operators that you can use in Lattice Boltzmann, but the only one that we have now introduced was the BGK operator. And what is true for the BGK collision operator will also be true for other collision operators, usually. So the BGK collision operator, how did it look? It is we write the operator as an omega. In some literature, it's also called C, for example, or different names. We write it as an omega here. And we say this is the, so for a particle direction I, yeah? So this is the population after the collision minus the population before the collision, right? This is the definition of the collision operator. And in BGK, so this the first one is general, and what makes it BGK is when we write this is the frequency omega times Fi EQ, so the equilibrium, minus Fi the input. So this, because Fi is the input, so Fi is known before, and from this, if we bring the Fi that is on the left-hand side to the right-hand side, we can calculate the post-collision from the pre-collision. Yeah. So this is in this sense, say algorithmically, if I may use that strange word, algorithm. Explicit. Yeah, because the F star, the post-collision, just depends on what we had before. But F star and F, as we said last time, they are not the F from the Boltzmann equation. So we get the F from the Boltzmann equation by a change of variables. So Fi, and we can express Fi, the pre-collision state, so this we had last time, as Fi half minus Fi star after collision I, plus Fi bar. And this Fi bar is the distribution function that appears in the Boltzmann equation. So this is the actual variable that we would have to solve for in the Boltzmann equation, right? So, and this, of course, depends on the pre and the post-collision state. And if we plug this into our explicit equation here, so we have omega then Fi EQ, so we plug it only on the right-hand side, right? So we plug it only here on the right-hand side as Fi bar minus Fi minus Fi star divided by 1/2. So this is simply taking taking this guy here, yeah, and replacing it with this thing here, right? So, and then we see that on the left-hand side, we have this implicit thing, because this is implicit, because we have the same thing here, right? And now we take this to the other side, so this is implicit, but it's linear, so we can just resolve it, right? So it's fi x minus, not x, fi star minus fi. So we take this to the other side, and then we divide by it again, and this would be 1 over omega minus 1/2. So this is something that we had last lecture. So, and now this is actually implicit in the implicit in fi bar, which is the actual correct variable, right? So what we had is, this is algorithmically explicit what we're doing, yeah, but it's mathematically implicit. So it's implicit from the point of view of solving for fi bar. No, I write f usually differently, right? Like this. Okay, right? So we have now an algorithm that is completely explicit, but what it does, it solves an implicit function. Yeah. So what we have is explicit algorithm solves implicit equation. So this is something extremely important, and this is the reason why Lattice Boltzmann exists in the first place, because without this there would be no point. Yeah? And the reason for this is, what is the difference between implicit and explicit functions? The thing is, if we have, numerical methods, is that when we have an implicit method, implicit time marching methods, they have no time step restrictions, no intrinsics, let's say. Okay, I notice I'm a little bit hand waving here. Oops, time step. Okay. Yeah, you appear to look a little bit confused. When you solve a time marching problem with an implicit time marching scheme that depends on the outcome, yeah, then this will not become unstable because you make your time step larger. Like you use an Euler backward, yeah? You make your time step larger, it's not going to be unstable. However, when you make Euler forward, you integrate from here in time, and you are completely explicit. Then this method will blow up, it will become unstable. So you have you have to restrict your time step. And in particular, you would usually have to restrict your time step in a sense that is related to what you are doing. So obviously, if you want to resolve, if your problem is the collision of particles, yeah, then you have to be smaller than the time between the collision of the particles to actually resolve them. Otherwise, you're not doing physics. Yeah. So this is so in explicit methods, this restricts the time step that you can use, but now in an implicit method, this at least stays stable when you use larger time steps. It does not necessarily mean that it's still correct, but it means it is stable. Yeah. So what's okay? Let us look at what it actually mathematically means. Because now we have the following. Our tau. The tau, which is the mean free time between collisions. Yeah? This can be expressed now as 1 over omega minus 1/2 delta t. Okay? So this is what we just discovered. And this means that in this implicit world, that is what we have in Lattice Boltzmann. Yeah? And when we turn this around, yeah, so we get delta t divided by tau plus 1/2 delta t. Yeah, so this would be omega, an implicit scheme that actually is LBM. Right. Now, imagine you solve the Boltzmann equation with a different discretization that does not have this distinction between pre-collision and post-collision. So suppose you do it correctly from the beginning. So you start from F bar from the beginning, yeah, and you implement an explicit scheme. Then this omega explicit, yeah, so you don't get any transformation here. And then you would simply have, so there's an equal sign missing, you would have delta t divided by tau. Okay, let's very briefly go back. Suppose this here, yeah? The original equation would be discretized with F bar in this place. Yeah, so we would already discretize this with F bar in this place because this would be correct, right? Yeah, and this here is actually incorrect in a sense, yeah, because this is not really BGK, yeah. This is BGK with an F that does not exist in physics. Yeah, this pre-collision state, this is nothing that exists in physics. So we would have to put the bar here. I will remove it because I don't want to. Now we have implemented BGK with the wrong F in this place. And suppose we implement it with the correct F, then we would have this explicit. Then this omega would just be delta t divided by tau, right? So if we start from the right thing, then this would be then it would look like this. And this would cause us some trouble, because now suppose, and I mean this is the very point, this delta t, we said that tau is of the order of 10 by the power of minus 10 seconds. Yeah? So we don't want to resolve this, so we take a delta t. Delta t is the time step of our method. Delta t we take this very much larger than tau, right? So if we take it very much larger than tau, what happens to omega implicit? What happens to omega implicit is if this tau is extremely small, what we have left with is delta t divided by 1/2 delta t. So this means that omega will go to 2, right? So in the algorithm, we have to put omega somewhere close to 2, which in a sense doesn't sound to be too problematic, right? Yeah, we have to set this to 2. What do we have to do if we have an explicit scheme? Omega explicit. So tau is going to 0. Tau is going to 0. This goes to infinity. So from the implementation point of view alone, right, you would have to multiply this. So in one case, in the implicit case, if the time step becomes insanely large, all you have to do is you multiply the non-equilibrium part by 2. In the other case, you have to multiply it by infinity. Yeah? So it's easy to imagine that multiplying things by infinity is not going to give you a stable method, right? But multiplying things with, it's not even possible. Yeah? But multiplying things by 2 actually gives you a reasonable method. So for example, let's look at this. So if we have Fi star, so this would be the pre-collision plus the collision operator Fi Eq minus Fi. So what happens if omega is going to 2? Then all you have is Fi star would be 2 times the equilibrium function minus Fi. So, and these are all things that are of similar order. Yeah? So we say this is well conditioned. This is well conditioned even for the case that delta t is much larger than tau. So well conditioned means that all the things that we something is badly conditioned if you add 2 numbers of which one is very large and one is very small. Even though algebraically everything is fine, computers have floating point numbers, and if you try to add up 2 things that are very different in size, you're not getting the right result. In particular, if you do this millions of times as you do in a simulation, right? But here, what you see is you have these things of similar size, and even if your time step goes to infinity, you just have the equilibrium twice and the incoming distribution once. So they are of very similar size. So, but what have we actually done? We've taken omega larger than 2, and we call this, so we do a distinction here. We call this regime 2 larger than omega, larger than 1. This we call over-relaxation. And let's have a look what this actually means. So say we have now some space. For example, if we some space in which we have the different populations, F alpha, F beta, or something, yeah, where we have an incoming point. So the space this is the state space of your distribution. So it's, for example, if you have a discrete distribution with say we have 9 discrete populations, yeah, so this would be a 9-dimensional space. Yeah? So, or you could write this down in moments, then it would be a different space, but it would have the same meaning. Yeah? So in this space, there is an incoming distribution. There's just a point in the space, a point in the state space, and we have an equilibrium distribution, which is a different point in the same space. Yeah? So, and then we also have the outgoing distribution, and this is what I want to draw here. So what BGK does is it does a kind of interpolation along this line, right? So this omega controls the length of the line. So for example, if omega is equal to 1, right, then the outgoing, so if omega is equal to 1, if you go back to this guy here, if omega is equal to 1, then the post-collision state will be the equilibrium state, right? So we'll end up on this point here. If omega is now smaller, okay, now I do it the other way around because I want to write this in red. So if omega is larger than 1, your post-collision state will be somewhere here. And if omega is, say, omega is smaller than 1, then your post-collision state will be here. You get what I mean? So, and if it's larger than 2, so this here is over, relax, and the other one is under relax. So under relaxation basically means that your time step would resolve the mean free path, the mean free time. Over relaxation means you are not resolving the mean free time. And in order to do this, you don't go close. I mean, you are going closer to from the input to the out, from the in state to the out state, from F to F star. You go closer to the equilibrium, but what you are actually doing is you are going beyond the equilibrium. You still need to be close, the end point still need to be closer than the incoming point, yeah, but it's not on the same side. So if you have an explicit scheme and you resolve the mean free time, you're only getting closer to the equilibrium on the same side of the equilibrium on which you are currently are. But what we are doing now is we're going beyond the equilibrium, yeah? So the non-equilibrium part that we had previously is going to be inverted, in a sense. And this, okay, I have to write down that, one larger than omega larger than 0, this is under relaxation. Okay, so the good thing with this here is that our method is linearly stable in the range of omega as 0.2. So without 2 is not stable. So 2 is marginally stable. And for omega larger than 2, it is actually unconditionally unstable. And if you look at the equation, it's also pretty easy to see why, because this gives you a negative mean free time. So basically what you do if you take omega larger than 2 is you're running the time in the opposite direction. Yeah, so you're no longer generating entropy, and therefore you're breaking the ether theorem in that sense. Yeah, so this cannot be. So you would try to get information from nowhere in a sense. So you have a resting fluid, and you want to see the swirl going larger because you run. I mean, this is like you're swirling your fluid, let it rest, and then when you invert the time direction, you would expect that from a resting fluid you get the whirl back, yeah, and this is of course lost information, so it's not possible. So this is why this will be unstable if you go here too far. Okay, now this is the reason why Lattice Boltzmann exists. Okay, I have a few more words here. So the stability bound for an imaginary explicit, so this is not what we have here, for real explicit BGK, I mean, this is now not LBM. Yeah? This is when we did it in another way. Then we would have a delta T of about 2 tau about 10 by the power of minus 10 seconds. And the stability limit of our now implicit method is different, because the stability limit is no longer given by the collision times. Say for our implicit BGK, is then the CFL condition. Of the streaming operator. So we have to make an important distinction here, yeah? What we made implicit is the collision operator. The collision operator is now implicit. The streaming operator the collision operator is implicit. The streaming operator is still explicit. So the streaming operator still has a stability bound, and the stability bound is the CFL condition of the streaming operator. So do you know what the CFL condition is? Yeah, you know. Yeah, it's Courant, Friedrich, Levy. So these are the three people who is. I think it's probably more or less exactly 100 years old. Yeah. So the CFL condition just says that information in the equation cannot travel faster than the information travels in the numerical scheme, and the information traveling in the numerical scheme is usually related to the advection of the fluid or the transport of the fluid, and the fluid is transported in two different ways, namely by its velocity and also by its speed of sound. So you have to, so if your fluid is Galilean invariant, yeah, So when it's moving, then the actual velocity of moving information will be the velocity of the fluid plus the speed of sound on top of the fluid. Yeah, because if your fluid is moving, then the sound speed is also moving together with it. Yeah, so if the air is coming towards you, then also the sound, which is usually coming with 340 meters per second, or say, okay, the speed of sound is 340 meters per second, and you are moving towards the source of the sound with, say, 50 meters per second, yeah, then actually the information that is coming towards you is 340 plus the 50 meters per second, so it's 390. So this is why we have to add to this to the advection to the average velocity of the fluid, the speed of sound, and this together. Now this cannot move faster than one grid spacing by one time step. So this is the CFL condition. Yeah. So the condition that we now have is that delta t must be smaller than delta x divided by u plus cs. This is our new stability condition. So if you break this, this will also break Lattice Boltzmann. So this means, okay, important thing to note is that in an explicit Boltzmann solver, the time step restriction depends on the mean free time. So it's independent of for example, the spatial resolution. Yeah, so the mean free time is no longer in here, but we have the spatial resolution in here. If you make the spatial resolution larger, then you can have a larger time step, right? And it's even linear. So you make it 10 times larger, you can have 10 times larger time step. So, so say we have a delta x is equal to 1 millimeter. For this could be many examples would have this kind of resolution. And say now the velocity for simplification, I just ignored this velocity, so I say this is 0, which is of course, if it's usually not 0, and then the time step restraint would be a little bit smaller, but let's just back on the envelope calculation. Say we put this in, and then we have 3 times power of minus 6 seconds. So, which is, you see, 4 orders of magnitude larger than you would have with the Prior-Boltzmann equation. Yeah. Okay. Okay, a little bit of text, and then I noticed that I'm talking too much because we are running out of time. So the reason for this bound is the explicit streaming operator in Lattice Boltzmann, which we cannot get rid of so easily. And usually we don't want to get rid of it because it's efficient. So you can even improve on this by rescaling the Mach number by saying, okay, we're not caring about that the speed of sound is exactly 340 meters per second. This is very often done, and then you actually have even more convenient time steps. So, and of course, the most important point is that LBM is efficient only due to over-relaxation, only because we can do this here. Otherwise, this would be ridiculously inefficient. So actually in the 90s, the company that sold the first Lattice Boltzmann solver made a patent on over-relaxation. I don't think that this patent has ever been enforced, and it's probably also now run out of, the time is like 35 years or so old. The thing is that over-relaxation is, of course, well known in mathematics. So the very idea that you can make a patent on this, and that actually the US Patent Office granted this patent is kind of ridiculous, but there is such a patent. Yeah. So this is using over-relaxation in order to get to make this algorithm efficient. So kinetic methods tending. Okay, so there's one picture that I want to introduce now. Kinetic methods tending to the Navier-Stokes equations for delta t much larger than tau are called asymptotic preserving. So this is not the only method that has this property, and is even sometimes not completely clear whether it has this property. But this is one thing that you may come across if you study other kinetic methods. And so the message behind this is now the following, and this was the picture on the start of the lecture. Say we have a discrete Boltzmann equation. So discrete Boltzmann equation is one with discrete velocities. Yeah, on one side here. So this discrete Boltzmann equation with a discrete time step. So if you make the time step small in your discrete Boltzmann equation, what you want to obtain is you want to see the solution of the Boltzmann equation. Right? So the better you make your approximation by making the time step smaller, you will finally converge to the equation that you are solving. Yeah? Okay, now this is time step. We also have the Knudsen number, and we know the limit. We know the limit of the Knudsen number squared to 0, and Knudsen number itself to a constant or larger than 0. Yeah. So if we go, or let's say we have this on the other side too. Yeah. So Knudsen number squared to 0 and Knudsen number to a constant. So if we start. So we can start from a discretization, or we can start from the Boltzmann equation itself. Yeah? When we start from the Boltzmann equation itself and we make the Knudsen number smaller, so what we end up is the Navier-Stokes equation. And if we have a discrete Boltzmann equation and we make this Knudsen number smaller, so we look only at the leading order moments, yeah, we get the Lattice Boltzmann method. Now, the asymptotic preservation is now, the thing is that if we make delta t, or I've forgotten here the 0, delta t, if delta t is going to 0, then we end also up with the Boltzmann equation. So, and the meaning of asymptotic preservation is that that the discretization still allows you to have the limit. Yeah, because this is absolutely not clear that you could that you can take the way with first taking the Boltzmann equation to a finite number of Knudsen numbers, or the discretized Boltzmann equation to a finite number of Knudsen numbers, and when you then go to infinite resolution, you end up with the same equation to where you are coming to when you start from the Boltzmann equation itself, and when the method has this property, we call it asymptotic preserving. Okay, so this is just, yeah, I have to go on with a little bit more practical things, I think. Okay, I just a few notes. LBM has the same time step constraints as an explicit Navier-Stokes solver. So there is a lot of nonsense around in the public domain, because now the people coming from the kinetic side, they often say, okay, so you have a time step constraint because you're in a kinetic, you have a kinetic solver. And then some people say, oh, we don't have this time step constraint, so Lattice Boltzmann has no time step constraint. And this would be better than the Navier-Stokes equation, because the Navier-Stokes equation has a CFL constraint. Now what it turns out is Lattice Boltzmann is not better in that sense, yeah, because it does the same thing. It has the same time step constraint, so you can have the same sort of time steps as with the Lattice Boltzmann, with the Navier-Stokes equation. It's actually pretty similar. And the one thing that you have to also keep in mind is that by taking this over relaxation, you also lost the physics. You lost the kinetic physics, okay? So you don't have the restrictions, but you don't have the information. Yeah? So because you're integrating over your collision times away, yeah? So you're not looking at the collisions, yeah? You're doing over relaxation. This is something extremely abstract, yeah? It's not resolved, and if you don't resolve it, it's no longer included in your result. So you don't pay for it, but you don't get it, right? So this means that you're actually not much better than doing straight Navier-Stokes equation, but there is a little bit of kinetic legacy, and this legacy is the linear advection operator. Because in the Navier-Stokes equation, the advection operator is nonlinear, which causes a lot of problems. And here in Lattice Boltzmann, you still have a linear advection operator. And one sentence that you may often hear is that in Lattice Boltzmann, all the nonlinearity, which of course exists, all the nonlinearity is local, and all non-locality is linear. Okay, this is not a sentence, but anyway, this is a statement that you should remember. Because this just simplifies the implementation of such a method. Okay, now we come to if you don't have any particular questions, I know this was very dense stuff, then we come to the second part of the lecture today, which I believe is a little bit more straightforward. And in particular, it's important now for the practical purposes, which is the discrete equilibrium distribution function. And the different ways we can do this, and I have to speed up because I have 3 pages left and with more than half time. So we have different ways of deriving the equilibrium function, which we need, for example, in the BGK collision operator. And this can be done by the moment matching, the Taylor expansion, and by entropy minimization. Probably I'm skipping over this. Okay, so let's look at the different ways we can derive our equilibrium function, because this we need for implementing the Lattice Boltzmann methods. So far, this was something completely abstract. Now let's look at the Lattice Boltzmann method, the one that you would also need to use in your homework. 2-dimensional Lattice Boltzmann method with f minus 1, 0, f1, 0. Okay, I'm not writing all of them, just some examples. And this thing we call the D2Q9 velocity set or lattice. Okay, and for this we want to have equilibrium distributions. So how do we get the equilibrium distributions? Well, we have the definition of our moments, MAB, which we call the sum over ij if I and j over I by the power of a and j by the power of b. So this is how we define the moments. Now we have 9 of them, obviously. And what we do is we match each of the moment that we have with a moment from the Boltzmann, from the Maxwell-Boltzmann distribution. So this looks like this. There are conserved moments, which say this is rho. So for the equilibrium, conserved moments is pretty simple, because what we have before is the thing that we have after in the equilibrium too. It just gives different names. So M00 is rho, the density, and M10 is rho times ux, and M01 is rho times uy, and these guys are conserved. So 3 gone. Then we have the second moment, M20. Now this is not conserved. This is why I write now equilibrium. And this in the Boltzmann equation is rho times cs square plus ux in the Maxwell-Boltzmann distribution, I mean. And the other guy, M20 equilibrium, is rho cs square plus uy square. Okay, the other moments are, can be again directly matched with the moments of the Boltzmann equation, but there's one simplification I want to highlight here, namely the Maxwell-Boltzmann distribution. This is what I mean with the Boltzmann equation. Now, the Boltzmann, I should be more careful, because the Boltzmann equation would be the Boltzmann transport equation. Yeah, so I mean the Maxwell-Boltzmann distribution. Yeah, sorry for being confusing here. Yeah, so this has the symmetry property that it can be factored in its different velocity directions. Yeah, so this comes from the independence of The reason for this is because what it means is that the different variables x, y, and z, they are independent random variables of each other, and they are independent random variables if their distribution factor. So if the mixed probability is the product of the individual probabilities, and this is something that translates also to moments. And this means, for example, that the moment M11 equilibrium can be expressed as the moment M10 times M01. However, because we have not normalized these moments and distributions, the distribution would be normalized. Integral is 1, right? So because we did not normalize it, we have to normalize it here by dividing by rho. So this is how we can quickly write the. We can quickly write the equilibrium of this second order moment, and for the other guys, it is the same thing. So, for example, the third order moment equilibrium is equal to M20 equilibrium times M01 equilibrium or not equilibrium, because they are the same, divided by rho, and this gives you ux, no, this is uy, sorry, uy, ux square plus cs square times rho. I've forgotten to write times rho here in my notes. And M12 equilibrium is then, of course, M10 equilibrium times M02 equilibrium divided by rho, and this would be ux uy square plus cs square times rho. And then there is one last one, then we have 9, is M22, and this would be M20 equilibrium times M02 equilibrium divided by rho, and this is ux square plus cs squared times uy squared plus cs square times rho. Okay, so this is what we call so these are the moments, and we know that there's a linear transformation between the moments and the distribution. So all you have to do is now to solve this set of equations, which I'm not going to show. This is something that you could do as a homework. What we notice here is that in this we have, there's not everything is appearing in this, in particular some third order in velocity terms are missing from these, and this would be ux cube and uy cube, though they are nowhere in this equation, and so they will be not in the equilibrium. So they are missing, but on the other hand, we have something that is larger. Ux square times uy square, or actually, okay, from a mathematical point is smaller. So it's a higher order, say. So this guy is present while other guys are not present, and this actually means that the equilibrium that comes out of moment matching is anisotropic. Okay, I have to tell you that this is something that you should not worry too much about. It's just a property. So people have been more worried about this than was necessary in the past. Okay, so this is one version of getting the equilibrium. Another version of getting the equilibrium is the Taylor expansion. Of the Boltzmann distribution. To second order in velocity. So this is something that doesn't really have anything to do with the particular lattice. So this can be written down directly because it always looks the same. The only way where the lattice is coming in is by the so-called lattice weights, which we call as Wi. Rho then comes 1 plus EI, so this is the velocity. EI is the velocity of the particle of the distribution I. And you already noticed that this is not the standard nomenclature that we are using here. So there's only one index, while we are using several index. So you can put, so they put everything in one vector, yeah? And then of course you have to have a given ordering, and the given ordering is indicated by the value EI. So this is the velocity of this particular direction. So as you see that this is a nomenclature that we are not using here. You already noticed that we are also not using Taylor expansion here usually in the lecture. But I have to mention this because it's very common, and it would be strange if I let you go without mentioning this. So the Wi, these are weights, and they are obtained at velocity 0 and rho equal to 1. So I personally, if I would want to know these weights, I would calculate them from moment matching, because this is the easiest way to do it. But you can also explicitly take the Taylor expansion of the Boltzmann equation here, apparently. So it's not the Boltzmann equation, the Boltzmann distribution, the Maxwell-Boltzmann distribution. Okay, so this thing here is actually isotropic, which some people think is an advantage. It's isotropic, but it's missing higher order terms in velocity. So one advantage of this is that it's pretty independent of the lattice. So when you have moment matching, yeah, so you get for each additional direction you get one term more. So your equilibrium will obviously depend on what velocity distribution you are actually using. This here actually does not depend on the form of your velocity distribution other than there is this weighting factor. This is the only way it would depend on your actual on your lattice. So one thing here to know is this is the classic way to do it. So it's classic, is so to speak the text, book, style, equilibrium, however, this is nowadays getting less popular because people have noticed that it's not stable, or it's not so stable. Due to the better stability. With moment matching. So moment matching is getting more popular, and this is going to get less popular. So I was saying I want to introduce the entropic method, so I'm actually inclined to skip over this. Now I started writing, so I will very briefly introduce it. This is, okay, let's have, so this is the aim, is to enforce an Esser theorem, which as it turned out doesn't really work. And I have to admit, I noticed that in the last 10 years nobody was speaking about these things. This is also why it's probably not so important, but for completeness, I usually don't ask a lot about this in the exam. So it's the equilibrium is coming as a strange function that, if I now just write it in correctly, hopefully, I don't know, 2u alpha plus c times c alpha s alpha divided c minus u alpha c alpha divided by c, with alpha either being the x velocity or the y velocity. C is delta x by delta t, and s alpha is 1 over, is the square root of the velocity in that particular direction divided by c s square. Okay, so this is the equilibrium that they are using. And they claim that they proved the Esser theorem for this. And this is supposed to guarantee stability However, in practice, only stable with additional an additional limiter called entropic time stepping. So they claim this is always stable, but it's actually not, unless they put a limiter on top of it and kill basically the viscosity. So if you want to know why you don't want to know this, then you can look into Physical Review E83056710, where it was analyzed more than 10 years ago, and I think this is the only paper you will ever need to read about this. So I mean, if you come across this and you read, okay, this is supposed to be something very interesting and very good. So remember, I told you, I mean, you can look into this, but don't get too confused about this. This is more or less, you know, disproved. It's like a little bit of fake improvement. The authors themselves don't use it anymore. Okay, kind of 20 minutes left. Let's go from these lattices that we had now in 2D, let's go to lattices in 3 dimensions. So this is also something that we briefly discussed last time. So we have only, so at the very end, where last time we talked about only the one-dimensional case, right? Where we have a distribution, the population staying here, one going to the right, and one going to the left, and this was in 1D, and we call this V1Q3 lattice. Yeah. So, and then when we want to go to higher dimensions, what we start out with is the so-called tensor product lattices. So, for example, in 3D, this would be D3 Q3 by the power of 3. So it would be D3 Q27. Yeah? And now we have to look what are the countable moments for this guy. Countable moments. So for the tensor product lattices, so tensor product lattice means we put in every place where we have distribution in one direction, we take the same thing perpendicular and put the same distribution in the other direction too, right? And we do this 3 times. Yeah? So this is where we get 2, 3 by the power of 3. So, and the good thing is then we can easily see what are the moments, because the moments also kind of a tensor product. So the moments that we have now have 3 indices, right? And the moments that we have in one dimension, this was 0, 1, and 2, right? And now in a tensor product, we have each of them 0, 1, 2. So it's pretty straightforward to say what are the moments of this tensor product lattice. Yeah? So let's still write it down. So we have one guy with all of them 0. We have first moments like M 1, 0, 0. Yeah? And this now we can permute these indices, so we'll have this 3 times, obviously. Yeah. So second moments, we have 2 different kinds. We have 2 different kinds of second moments, namely M110, and if we take the permutations of this, you see that there are 3 permutations of this guy, right? And then we have M200, and also of this we have 3 permutations. So then we have third moments. So for example, M210. So how many permutations of this? Okay, if I had more time, I would. How many? 3. No. You can have more permutations of this because all the indices are different. 6, right. So it's 6 permutations of this, and then we have M111, and of this, of course, we have only 1 permutation, right? So then we go up to forced moments. up to fourth moments, and so we have M2 here, right? So out of this, how many permutations? 3 permutations of this. How many permutations of this guy? Also 3. So, and then we have fifth moments. M2 to 1, how many permutations? 3 permutations of this, and 6 moments M2 to 2, so how many permutations? Obviously 1, right? Okay, so this okay, so this is what we have on this lattice, and one thing that we notice is it's kind of too much, yeah, because the Navier-Stokes equation requires the full moments, as we discussed last time, the full moments. So the full moments would be the non-equilibrium plus the equilibrium. Those are the full moments up to second order. And third moments, we only need to have the right equilibrium. To a certain order, actually, only. This is something that we learn next week. So this means we have a lot of information in fourth and fifth and sixth order moments, which we do not need. And these things are given a name. They are non-essential as far as the Navier-Stokes equation goes. And therefore, they are called, so the non-essential moments are called, even in literature, they're called ghost moments. So here we have the ghosts. So there are 2 points, 2 negative things with ghosts. So you don't like ghosts. I don't know why people don't like ghosts. Yeah, ghosts, one thing is you have to feed your ghosts. Ghosts are considered a waste of memory because these ghosts, they have to be stored. They exist, yeah, somewhat. But they do not contribute to the Navier-Stokes equation. So actually we don't want them. And if the ghosts are bad ghosts and they become unstable, then everything else becomes unstable too. So they are also a risk for stability. And therefore, there are attempts to eliminate the ghosts by pruning. So, and now I have a little bit of problem because I just noticed that I wanted to copy a picture in this lecture, and I don't have this picture right here, so I have to briefly dig it up. From the previous time I made this lecture, right? So, oh. This doesn't work. And it doesn't work to copy it. This is, if you have only 10 minutes to finish your lecture, then it's of course completely annoying. Okay, you know what, okay, I show you the picture now here. Yeah, so there are different ways of pruning. We call it pruning. So pruning is you're cutting off, branches of your tree that you don't want to have. Yeah. So you can prune in different ways. the lattice by eliminating, for example, the velocities that go to the corner or that go to the edges, or actually only leave the one at the edges, right? So you take out some of the velocities, yeah, in order to reduce the set of moments that you have to deal with, yeah, and in order to reduce your decrease of freedom, for example, from 27 to down to 13, for example, yeah. So okay, what I'm going to do is I'm going to copy this in the notes. I leave here some space, and when you download the notes, it will be in it. Okay. So this is pruning. I leave some space. Now what we still need to remind us is that the number of moments, this is of course infinite, right? We can compute infinitely many moments, but we have only a certain set of independent moments. And this is also very clear, namely the number of independent moments is the number of lattice speeds, because it's a linear transformation. It's a linear transformation, so the number must be the same. Yeah, equations and the variables would be the same. So this means that the dependent moments are determined. We have dependent moments because they are not independent, and they are determined by moments of lower order. So this means that a moment, as we already said last week, appears again at a higher order as a so-called alias. So it has a second name. And we call these things here, because we are crazy, and we already called the other guys, we called them ghosts, so now we call them aliens, right? So these two things have to be distinguished, the aliens and the ghosts. So take this D3Q27 lattice with the moments being MA, BC equal to the sum over IJK, Fijk. So we use three indices here, I by the power of A, J by the power of K, and A by the power of B, A by the power of B, and K by the power of C, right? So then this M220, this is an independent moment, right? But it is a ghost because it does not appear in the Navier-Stokes equation as a fourth order moment. So this is a ghost, yeah? M300 for this lattice, because this is identical to M100, this is an alien. And M320 is equal to M120, so this again is an alien. This again is an alien. Okay, so for the Tensor product lattices, this is pretty straightforward. To see what is a ghost, okay, so this is anyway straightforward because it's the moments of higher order than 3, yeah, and or higher order than 2. And what the aliens are is also straightforward. This is whenever you have something that is larger than 2 in one of these indices. The picture is not so clear for these pruned lattices, where we've taken some speeds out in order to reduce our the number of variables that we have to take care of. And then it becomes a little bit unintuitive, actually. So let's look at the independent moments. One of the very popular lattices, D3Q19 lattice. So they have this independent moments M00, M100 3 times, M110 3 times, and M200 3 times, which is good because if they didn't have these, they would not solve the Navier-Stokes equation. So we need these. So, but now comes the ghosts that we don't actually need, and this guy here has 6 permutations, and then we have also M220 with another 3 permutations. Yeah, so we have reduced this, but the question is, how do we actually know originally that these are the moments? So the good thing is the lattices always look the same thing, so you have to solve this problem only once in the entire history of mathematics. So it's not a thing that that is so difficult in principle to do, but we notice that this is not completely simple by just looking at it and saying, okay, so this is the way to do it. So no simple methods to determine independent moments. Okay, so this is a negative sentence, so I actually don't want to stop on this, and I want to tell you how it has been done. For this, I will take again 4 minutes longer than I actually have now, but anyway. The way it was done historically, or can be done, if you need to do it, you can do it this way. You find an arbitrary ordering, an arbitrary ordering or enumeration of your distributions. I don't like arbitrary things. This is why I'm usually not using this, but this is very commonly used. So of the populations, so F alpha. So the point here is they have only one index now, right? So, and you put these, so alpha is an element in the 1 to Q. Q is the number of populations that you have in your distribution. Yeah? And they come with a velocity vector that is indicated by Cx alpha, Cy alpha, and Cz alpha. So you get an arbitrary ordering, and then you add a map saying this guy has this velocity, right? So, because this information has to be stored somewhere. So, and now you can compute the raw countable moments in the following way. So there are countable moments. M, A, B, C is the sum over alpha, EX alpha by the power of A, EY alpha by the power of B, EZ alpha by the power of C. So these are the vectors here, and you sum only now over alpha, not over the different directions. And if you do it this way, you can both express S alpha, F alpha, and the product EX alpha E by the power A, EY alpha by the power B, and EZ alpha by the power C. They can both be expressed in terms of vectors. So, and the way they do it is also very funny. They use different kinds of vectors, the so-called bracket vectors. So they use so-called pras, a pra vector. So this is now a polynomial BIBC. So this is what we call a pra vector. This is a lying vector. And this lying vector has the component x. So it's the velocity components in it. So for the first distribution in our list, and this goes up to the last. So Q is the last one distribution velocity in our list. In E Z Q C. So. Okay, so this is a lying vector, and this is combined with a standing vector, which we write in the opposite way, F alpha. No, not F alpha, F. So, and this contains, so this is a standing vector, F1 to Fq. Okay, and the nomenclature that is used is we can do a scalar product of the two guys by taking this P, A, B, C together with F, yeah, and this is a scalar, this is the definition of a scalar product in this nomenclature. Okay, so this is unfortunately the way this was done. This is the moment generating vector. So now what you can do is you can take any of these moment generating vectors and check if the moment vector P, A, B, C is linearly independent of all moment vectors of lower order. What does mean lower order in this context? Lower order in this context means that the sum A, B, C is smaller, right? So for all the vectors where the sum A, B, C is smaller than the one we are checking for, and if they are linearly independent, then this means that the moment is independent. So, and if they are not independent, then it is an alien moment. So this is the way you can check this. Okay, how much? Okay, I've taken 5 minutes more than I had. Sorry for always doing too long. So any questions for now? I guess I'm going to stop the recording.